Hello everyone. In this video I wanted to tie together the concepts that we've learned in the past couple lectures, those being the special right triangles as well as the trigonometric functions, and show you how they fit into one another and familiarize you with some of the trigonometry problems you might encounter in your math class. And so to start off, let's just find the trigonometric functions for each of these special right triangles. And I'm just going to start off with the 45, 45, 90 triangle. No particular reason that we're starting off with this triangle, just, it's easier, I guess, marginally. And so, both these angles here, as we established in the last video, are equal to 45 degrees, or pi over 4 radians. If you want me to do a video on degrees versus radians in the future, please let me know in the comments. I think it's probably a bit too shallow a topic to do a full video on, but if y'all want it, I'm certainly not opposed to making it. But for now, I'm just going to assume that you know this. If not, there are plenty of tutorials out there. It's not that difficult. It's literally just a conversion ratio. But I'm rambling at this point, so let's get going. So we know the common ratios for this triangle from the last video are 1 on this side to 1 again on this side to root 2 in the hypotenuse. And so I'm going to label this side, theta, so I don't have to draw out pi over 4 each time. So what's the sine of theta? What's the sine of pi over 4? Well, you'll see. From either of these angles, the opposite side is equal to 1, and the hypotenuse is equal to root 2. Sine, of course, being the opposite side over the hypotenuse. So from that, it's just 1 over root 2. Or, if you wanted to rationalize the denominator, you just multiply both of these by root 2, and you'd get root 2 over 2. But both of these are equal to one another, and both of these are equally correct, at least for our purposes of demonstration. But that said, what's the cosine of theta? Well, the side adjacent to either of these is going to be 1. And the hypotenuse, again, is just root 2. So, cosine of theta for the 45, 45, 90 is also 1 over root 2. And this pi over 4 radians, or 45 degrees, this angle has the unique property that its sine and cosine are equal to one another. No other angle, this happens to no other angle, and so that's just an interesting math fact right there. Math's pretty interesting. Lots of cool stuff goes on when you really get into it. But that being said, what's the tangent of theta? So for either of these pi over 4s, the opposite side is going to be 1, and the adjacent side is also going to be 1. So that's just 1 over 1, or 1. And so now, let's find the reciprocal functions for all of these. Starting off with sine, the reciprocal function is going to be cosecant, or hypotenuse over opposite. So we've already determined that the sine of theta is 1 over root 2. So to find the cosecant, you just flip that, and you get root 2 over 1, or root 2. Same thing with cosine theta. And since it's the same thing, I'm not going to bother writing the full thing out. I think I'll get the picture. Secant theta is equal to cosecant theta. And finally, cotangent theta. What's 1 over 1? If you flip that, it's still just 1 over 1. And there you have it. Those are all the trigonometric ratios for the 45, 45, 90 triangle. And now let's move on to the 30, 60, 90 triangle. Let me just draw this out. These are not at all to scale, by the way. I'm just doing my best from approximation. So we have this 60-degree angle up here, or pi over 3 radians. And we have the 30-degree angle down here, or pi over 6 radians. That's a 6 if you can't tell. And since these angles are different, I'm going to label this one theta 1. I'm going to label this one theta 2. This is just arbitrary, so it's a bit easier for me to write out, but you can call these whatever you want in reality. So first, let's try getting the trigonometric ratios for this pi over 3 side. So the sine of pi over 3, which we've labeled as theta sub 1. Oh, I forgot to write out the ratios. That is my bad. So the side opposite to this, as we discussed in the right triangles video, is root 3. The side opposite to pi over 6 is 1, and the hypotenuse is equal to 2. So therefore, the sine of theta sub 1 is going to be the opposite over hypotenuse. So that's going to be root 3 over 2. The cosine of theta sub 1 is going to be equal to the adjacent side over the hypotenuse, or 1 over 2. And finally, the tangent of theta sub 1 is going to be equal to the opposite side over the adjacent side. So that's going to be root 3 over 1, or just root 3. And what about this other angle, this theta over 2? Well, the sine of this angle, again, is going to be the opposite over the hypotenuse. So the opposite in this case is 1, and the hypotenuse is 2. So that's going to be 1 over 2. The cosine of I don't know why I said root, theta sub 2, is going to be the adjacent side over the hypotenuse. The adjacent side in this case is going to be root 3, and the hypotenuse is, of course, 2. So that becomes root 3 over 2. And finally, the tangent of theta over 2, theta sub 2, I don't know why I keep messing this up, is going to be the opposite side over the adjacent side. So that's 1 over root 3. Or if you wanted to rationalize the denominator, root 3 over 3. And there you have it. And I'll leave the reciprocal functions to you as an exercise if you want to do those. Mostly for practice, but also because I don't really want to bother writing all these out, if I'm being perfectly honest. But now I wanted to do a couple of challenge problems to really solidify that conceptual understanding of the trigonometric functions. And so I just found these on, hold on, I messed this up. I just found this on a website. I'll link to it in the description. There are a lot more problems where you can get some extra practice if you want to do that. But for now, we're just going to do these two because I saw these and I liked them as sort of conceptual problems. So let's start with this first one. Can the sine of an angle ever equal 2? Why or why not? So in order to answer about this question, we have to think about what sine represents in a right triangle. So I'm just going to draw an arbitrary right triangle. Let's call this angle X. Let's call this point of the triangle A. Let's call this B. And let's call this C. And we know from geometry that the hypotenuse of a triangle is always going to be longer than either of the sides. So if we know that, hold on, Let's call this opposite. Let's call this adjacent. Let's call this hypotenuse, just for clarity here. So if we know that hypotenuse is always going to be greater than opposite, or rather it's always going to be greater than or equal to opposite, I'll get into that in a second, and by definition the sine of any angle is equal to opposite over hypotenuse. Well, if hypotenuse is always greater than or equal to the opposite side, then to maximize this ratio, you would want the opposite side to be as long as possible, and the hypotenuse to be as small as possible, so you can get the largest result from this. But the best we can do in that regard is where the hypotenuse equals 0. And so if that's the case, then sine of x is just going to equal 1. And that is the maximum extent that sine of x can ever reach. And I found this animation online of this angle sort of collapsing down here. And I wanted to point out a few things to help solidify this. Ignore this angle. Consider this one instead. You'll notice that as B approaches C, it gets wider. And this angle, BAC, it gets smaller. So what happens is eventually AB, this line segment, collapses to AC as angle X, as we defined it, this ABC up here, becomes 90 degrees. And if this angle is 90 degrees, and X is also 90 degrees, then that means this is 0 degrees. And the whole thing essentially becomes a straight line, where AB is equal to AC. And if this is to keep going, well then the triangle would sort of be redefined. Let me draw it out to help spell it out. So if you have B collapsing to C, and eventually, after it collapses fully, and it becomes a straight line where AB is equal to AC, or in other words, opposite side is equal to hypotenuse, you may think that that might make the opposite to hypotenuse ratio bigger, following the trend of as it collapses, this angle gets larger. But what happens is, this becomes the right angle of the triangle, and the triangle sort of flips. And this is X, of course, as B has shifted. And this angle, once it passes this point, no longer becomes 90 degrees, but rather it becomes smaller as you progress downward. And this is just sort of a rough example, but you'll notice that as it goes more and more down, this angle just becomes shallower. And so I'm going to go into this more in a later video, but what you'll find is that both sine of x and cosine of x are what you call periodic functions. So they cycle through a variety of values as you increase another certain value. And I know I'm rambling a lot here, but the point I'm trying to make is that once point B crosses the point where AB and AC, or the hypotenuse and the opposite side, are equal, that is the highest point, the highest ratio that sine will ever reach. And from then on, it just starts to get smaller again. And to tie that back into the question, since the greatest that sine can ever be is the opposite side equaling the hypotenuse, or being therefore 1, the sine of an x cannot equal 2 for this reason. The most it will ever be is 1, no matter what kind of triangle you're looking at. And I know I sort of rambled a lot there. If you have any questions, please feel free to post them in the comments. I know I'm not always the best at explaining things, but I'd be happy to get to you. My goal is for you to understand this, and if you don't understand this, then well, I will have failed my mission, and I want to succeed in that. So if you got any questions, please post them below. I'll try my absolute best to answer them. But anyways, let's move on to this problem 24. Hopefully this one's going to be a bit easier. So we have sine of x equals 1 over 3. Find cosine of x. Well, if we know two sides of the triangle from this sine of x already, we have the opposite side and the hypotenuse. So we can essentially construct 2/3 of this right triangle, since we have two sides out of the 3. Here's the right angle. I'm going to separate this so it's clear that we're working on another problem. And let's say this is angle x. So we know from this information given above that the opposite side is equal to 1 and the hypotenuse is equal to 3. So in order to find cosine, we need to know this other side, since this is the adjacent side. And to do that, we can just use the Pythagorean theorem. So if we have a squared plus this other side squared is equal to the hypotenuse squared. So if you square all that out, you get a squared plus 1 equals 9. And if you subtract 1 from both sides, you get a squared. Oh, sorry, there's no plus there. A squared equals 8. And finally, taking the square root of both sides to isolate that a, you get a equals root 8. And so now our right triangle is complete. We have all that information there. And since we have all the sides, we can find the cosine of x. Since cosine is adjacent over hypotenuse, then the cosine of x is equal to root 8, being the adjacent side, over 3, being the hypotenuse. And there's the answer. So hopefully those problems solidified your understanding a little bit of both special right triangles as well as trigonometric ratios. In the next video, I'm going to be going into the unit circle and exploring how sine and cosine relate to one another graphically and expanding the definitions thereof. So I hope you found this informative, and that's gonna end the video. Hope you all have a great day.